Chapter 4. Up, Up, and Away. Technological progress comes in fits and starts. For a while, not much happens beyond a steady development of what's already known or been invented. Then, all of a sudden, comes a breakthrough that wakes us up to an entirely new level. This happened, for instance, with the invention of the practical steam engine at the start of the Industrial Revolution. It happened again with computers, when mechanical devices were replaced by electronic ones, and then again, though less visibly to the public at large, when vacuum tubes or valves were superseded by transistors. It is it's the same in mathematics. A moment of inspiration can lift us into a realm of thought that we never suspected existed. When it comes to big numbers, really big numbers, one of the trickiest problems is how to represent them. We quickly get tired of writing long rows of zeros and welcome being able to show a big number in terms of powers of 10. Then we learn that beyond addition, multiplication, and exponentiation, there's a never-ending hierarchy of hyperoperations starting with tetration, repeated exponentiation. The trouble is that up to this event, the ways we've used to try to represent this hierarchy are the equivalent of old technology which hampers any attempts at progress. We've said that just as we can denote an exponential as the a to the n, so a tetration can be represented by. So far, so good. What co- but what comes next? The trick of moving to the n, but the trick of moving the n to the other side of the base number is to indicate tetration can be repeated for the next level of hyperoperator or the one after that. Some more powerful and flexible scheme is needed to notate numbers that are far larger than, than any we've encountered up till now. In fact, various such schemes have been devised over the past century or so. Some of these have been adopted by mainstream mathematicians and find their way into academic papers. Others are better known on the fringe of the subject and are most commonly used in popular level writings about big numbers, such as this book, or the web pages of Gogologists, mathematicians, both amateur and professional, who in the spare time study them and find new ways to present large numbers. We've seen that mathematical operations with which we're most familiar, addition, multiplication, and exponentiation, are part of a never-ending sequence called the hyperorganization sequence. Strictly speaking, this begins with the successor operation. Then it continues after addition, multiplication, and exponentiation with iteration, pentation, and so on indefinitely. Each successively more powerful operator amounts to merely the repeated action of the operator below in the hierarchy. A conventional way of representing specific operations in this sequence use H notation. For instance, multiplying 5 by 4 would be shown as. This indicates that we're dealing with the second of hyperoperator after the zeroth one, H0, and the first addition H1. Or take another example, H3 2.5. This third hyperoperator is exponentiation, so that H3 2.5 it means 2 to the 5 is 2 times 2 times 2 times 2 times 2 equals 32. After this comes H4 which is tetration or repeated exponentiation. H4 4.3 for instance is 4 to the power of 4 to the power of 4 equals 4 to the power to the 250 56 equals 1.34 times 1 at 10 to 154 approximately. A different but equivalent system of notation uses square brackets to indicate the level of hyperoperator and takes the form of A and B, using the examples we've just considered. In 1976, American computer scientist and mathematician Donald Knuth proposed another and again exactly equivalent way of writing numbers in the hyperoperator sequence. It's known as up-arrow notation. Knuth had already established a reputation as a leader in the field of theoretical computer science with his multi-volume work The Art of Computer Programming, the first part of which came out in 1968. He was also the first to publish a book on a new expansive system of numbers proposed by English mathematician John Conway, which includes not only all finite numbers but also all infinitely large and infinitely small ones as well. During a lunchtime meeting with Knuth in 1972, Conway had explained the ideas behind his extraordinary new number system. Knuth was immediately captive. The following year, spent at the University of Oslo during a week-long break from his work on the art of computer programming, Knuth penned an introduction to Conway's mind-bogglingly large collection of numbers, which Knuth christened surreal numbers. I believe it is the only time, but not that a major mathematical discovery has been published first in a work of fiction. Knuth's novelette titled Surreal Numbers: How Two Students Turned to Pure Mathematics and Found Total Happiness takes the form of a dialogue between a young couple who studied maths together at university and are now stranded on an island. The two come across stone tablets on the beach, which give them clues about how to construct Conway's number system, starting from the empty set, the set that has no elements of members, and a few simple rules. As Knuth pointed out, his main goal in writing the book, beyond explaining surreal numbers, was to give a feel for what research in mathematics is like. The two lovers don't follow a straight line in their path to understanding the surreal path, as in the real world of research, make mistakes and to retrace some of their steps before finding a better way forward. Knuth continued his adventures into deep dark number land by announcing up-arrow notation in a paper that appeared in the journal Science. A single up-arrow represents exponentiation. For example, 2 up-arrow 4 equals 2 times 2 times 2 times 2 equals 2 to the power of 4 equals 16. Two up-arrows take us the next rung on the ladder hyperoperators tetration. For example, adding another up-arrow brings us to the level of pentation. Now we continue evaluating from right to left. Evaluating this number give a power tower of 2 of Higgs 65,536. Even a tower of Higgs 5 produces a ridiculously big number with approximately 26,300 digits. Adding another 2 to the power of 30 dwarfs the googolplex. Yet there are still 65,530 more 2's left to go. How about the hexation of 2? How about the hexation of distance ought to be? So you will need to take to pentate to this mighty power tower of Hague 65,536, starting with 2. This would involve making a series of power towers with the result of each being the height of the next. First we have 2, then which is the previous power tower, and so on with the number of such power towers being itself a power tower of Hague 65,536, like the googolplex, which it makes appear ludicrously small. To arouse for couldn't be written out in the full of health in any computer memory that could actually be constructed, present or future. It's simply a number vast beyond the capacity of the universe to display in decimal digit form. Yet we can represent it very succinctly in the form of those 6 symbols. The result of applying up arrows depends strongly not only on the number of the result of applying up arrows depends strongly not only on the number of up arrows but also on the numbers upon which the up arrows operate. In going from, we went from 16 to 65,536. But let's say we change the 2 to a 5 and the 4 to a 3. In the case of single up arrow 5, up arrow 3 equals 5 to the 3 equals 5 times 5 times 5 equals 125. But the tetration, the value of 5 multiplied by itself 3,125 times, it approximately 1,611 times 10 to 2,184. Remember, the earlier tetration we look at 2 up row 4 came out to be just 65,536. So clearly, the size of numbers being treated as a dramatic effect on the rate of growth of the outcome. Imagine how much more spectacular will be the explosion in values when we move to pentation, represented by 3 up arrows. The mesmerizing scale of the tetrated and pentated numbers becomes even more evident when we bear in mind that numbers such as 2, 3, 4, and 5 are small. Imagine the result of the tetration, or the massively greater still pentation. Yet even these numerical titans are dwarfed by the outcomes if we move to hyperoperators associated with even more up arrows. You may be thinking, why on earth do we need ways to represent numbers that are so monstrously huge? Of course, there's no practical reason at all. There's nothing in the real physical universe that corresponds with anything anywhere near big near as big as the number we've just written out in full. Never mind all the decimal digits of 2, all the decimal digits of 2, 3 up arrows 3, when it's been completely unpacked. But we're not exploring the limits of the material world here. We're not confining ourselves to what's meaningful or useful from a practical standpoint. We're in the realm of pure mathematics, where the space available for containing and representing numbers in any way we choose is unlimited, and there and where there's no need to ask if there's any point to something just because it doesn't have a physical correlate. Not a Nuts up around notation is impressively powerful compared to anything else we've come across so far, but you can get but you can get just as tired of writing long lines of arrows as you can writing a lengthy string of zeros. Here, for example, is a perfectly valid number specified in up around notation. The mind freezes at what this might be, like if it were possible to write out as an ordinary number. But even so in up arrow form, it looks unwieldy. How many up arrows are there in the row? As it happens, there are 39. But the only way but the only way you could discover that for yourself is to count them, which is a pain. Far be far better to write it in the more compact form, so that we can know at a glance what we're dealing with. It's easy to see that up arrow notation is equivalent to the two shorthand schemes we mentioned earlier for presenting numbers in the hyperoperator sequence. The only difference is that up arrows start to be used only at the stage of exponentiation, so the number of the up arrows is always 2 less than h s2 less than h subscript, or the number in the square brackets of the other methods. Using the examples we look at when describing the edge operator square bracket schemes. Each of these each of these equivalent schemes involve what's called a binary dyadic operator, because it acts on just two elements, the numbers in the brackets after the edge operator, or either side of the square brackets, or on either side of the upper rows. As for the three different parameters, the level of the hyperoperator and the two elements acted upon, this can be referred to as the rank, base, and exponent, or hyperexponent respectively. So for instance, in H3 2.5, 3 is the rank, 2 is the base, and 5 is the exponent. In the case of upper rows, we need to add 2 onto the number of upper rows to get the rank. For example, if we have 6, 3 upper rows 3, the rank is 5 per augmentation, the base is 6, the exponent is 3, we could say 6, 3 upper rows 3 as the third permutation of 6. We can represent some terrifyingly big numbers in these three equivalent forms of hyperoperator notation. Number like are spectacularly fast, but take upon notation. But take up around notation. What if we keep adding much more up arrows, many more? For example, there's such a number as with 26 million trillion up arrows between the 43 and the 85. Now, the problem becomes keeping track not of the number of up arrows, but of the number of zeros telling us the number of up arrows. we could collapse the exponent after the up arrows to 26 times 10 to 42. But then we're getting back into the inconvenience and typographic nightmare of having to write exponents of exponents, and then of exponent of exponent of exponent, and so on, which returns us to the same situation we had before, and certainly wins you no friends among your publisher's production team. The fact is that even Knuth's up arrow notation eventually reaches a stage where it's impracticable. You won't be surprised to hear that other ingenious schemes have been devised for representing fantastically big numbers. One of these named Stenhouse-Moser. One of these is named Stenhouse-Moser notation after its creators, Hugo Steinhaus and Leo Moser. Steinhaus was a Jewish-Polish mathematician who earned his PhD in 1911 at Göttingen University under the supervision of David Hilbert, the greatest mathematician of his day. Together with his compatriot Stefan Banach, Steinhaus went on to discover one of the most important results in branch of maths, known as functional analysis. He is also considered to have been a leading light in the development of both game theory and probability theory. In his popular level book Mathematical Snapshots, published in 1950, Steinhaus suggested a way of representing large numbers using triangles, squares, and circles. He starts by defining a number n inside a triangle to mean n to the n. For example, next, n written inside a square denotes n inside n triangles. For example, finally, n inside a circle denotes n inside n square. N inside a cycle denotes n inside n squares. Continuing with our example in which n equals 2, we arrive at the result that Steinhaus got this number 256 inside a square, the mega. The question is just how big is it? The mega is the same as 256 written inside 256 nested triangles. The innermost triangle means 256 to the 256, in which in itself, written out in full, a pretty impressive number. Let's call this number n1. It has 617 decimal digits, and written in terms of power of 10 is approximately 3.23 times 10 to 616. It's obviously a heck of a lot bigger than a Google, which is a mere 10 to 100. As we've only just started to work our way up to the set of triangles within triangles in order to evaluate the mega. Next, we have to figure out the value of a 617-digit long number raised to the power of itself. That's not possible to compute because the answer has about 10 to 616 digits, a number immensely larger than the number of subatomic particles in the universe. And beyond this, we have 254 triangles to go. The mega, which appears so simple and compact when written as just a 2 inside a circle, is a monster in disguise. It makes the googolplex and skewest number look at most indistinguishable from 0. We can't know the exact value of the mega, but strange as it may seem,
It isn't hard, given a few hours computing time on a laptop, to figure out its final few digits. We'll never be able to work out the first digit of the mega or the first bulk of those that follow, but the last of them are known with absolute certainty to be for 42,656. The the 6 at variant, for instance, is easy to explain since it comes from multiplying 6 by itself many times in the computation at immense power to power of 256, and any whole number power of 6 ends in 6.
It's not hard, so although we won't do it here, that in terms of up arrows, the value of the mega lies somewhere between 10 up arrows 10 to up arrows 257 and 10 to up arrows 258. That may seem surprisingly modest. After all, we've been giving the mega a big build-up and illustrating how mind-blowingly hurts it when we work our way up to the different levels of its notation in Steinhaus form. Yet, its upper and lower bounds can be written quite compactly using up arrows. The mega is truly colossal based by the standards of the ordinary numbers with which we're used to dealing. The fact that just goes to show how powerful is the operation of the tetration compared with the more familiar lower lower order operations of addition, multiplication, and even exponentiation, and also how potent are nuts up arrows are as a way of representing large numbers in mathematical snapshots. Steinhaus named an even bigger number the megiston, defined as, and which, in terms of up arrows, can be expressed as a pentation with a value between 10 3 up arrows 11 and 10 3 up arrows 12. Australian-Canadian mathematician Leo Moser extended the notation devised by Steinhaus to include pentagons, hexagons, heptagons, and, in general, any polygon with x number of sides and any number written inside it. The Steinhaus-Moser system replaces the cycle with a pentagon and then uses polygons with more than 5 sides to enable a startlingly rapid growth in the size of numbers that can be represented. In general, a number n written inside an excited polygon is the equivalent of n inside n nested polygons, each with minus 1 sides. The number known as the moser is defined as 2 written inside a megagon. Here, we're using megagon to mean a polygon with a mega number of sides, distinct from its other meaning in conventional plane geometry, which is a polygon with a million sides. Remember that the mega is itself a colossal number somewhere between, and that we're now dealing with a mega-sided polygon. So it's evident that the moser is very, very big indeed. In, term, in terms of up arrows, the field of the moser lies between that breathtakingly large when you consider the awesome growth in size that comes the addition of each and every up arrow, and that here we are talking about a mega number of up arrows minus 2, whereas the mega is the tetration level number with a value between. The moser is so huge it enforced a tetration level number of up arrows. With the moser,
We've arrived at something new. A number that, expressed in terms of operows, involves a recursion of the number of operows. In art, music, language, computing, and math, recursion pops up in all kinds of different places, but always it refers to something that fits back into itself. In some cases, this just leads to an endless, repetitive loop. For example, there's the joke glossary entry, recursion, recursion. On a more elaborate scale, a recursion loop appears in Maurice Esser's Pingellery, 1956, which shows a gallery in a city in which there's a picture of a gallery in a city in which, in engineering, a classic example of recursion is feedback, where the output from a system gets routed back as input. It's a familiar problem for performers such as rock musicians on stage, and often happens if a microphone is located in front of a loudspeaker to which it connected. Sounds picked up by the mic come out of the speaker, having been amplified. They re-enter the mic at higher volume to be amplified again, so it goes on until, very quickly, the familiar sequel of feedback emerges. Recursion in recursion in math works along similar lines. A function takes the place of an electronic system, such as microphone, amplifier, loudspeaker combination, and calls upon itself so that it feeds its own output back as input. The well-known the well-known Fibonacci series is a simple case of mathematical recursion at work. The series starts with the number 1, 1. These are then added to give 2, and the series continues by adding the previous two numbers together to produce the Fibonacci numbers 1, 1, 2, 3, 5, 8, 30, 21, 34, 55. In the 17th century, German astronomer and mathematician Johannes Kepler showed that the ratio of successive terms in Fibonacci series approached a number that, like p, comes up a great deal in math, known as the golden ratio phi, which is approximately 1.618. In 1765, Swiss mathematician Leonhard Euler published a formula now called true misattribution for Wiener formula, showing that the Fibonacci numbers grow at an exponential rate equal to phi. Shapes known as fractals are produced by recursion. One of the defining features of fractal is self-similarity, which means that the whole object has the same or similar shape to one or more of its parts. A simple example is the Sierpinski triangle. It was the overall shape of an equilateral triangle and is constructed by repeatedly removing triangular subsets, as shown in Figure 4.2. From now, we are going to find the recursion is in one form or another is at the heart of most of attempts to represent and define even larger numbers. In the case of the moser, we see a number, the mega, described using arrows being used as the starting point for a recursive process that ends up specifying the number of arrows needed to describe the moser. There is nothing to stop us repeating the process and defining a new number, call it the monster moser. in terms of a Moser number of rows. Let's define the monster Moser to be. Why we stop there? Somewhere in the infinite space of mathematical cosmos is a number we'll dub the mega monster Moser equal to, and so on and so on. The point is the way the Morse is defined gives us an early glimpse of the power of recursion and what might lie far beyond the length of nuts up arrows. Of course, Steinhaus-Moser notation as a pictorial form of large number representation is impossible to use in practice, with the exception of a few simple cases like the ones we've mentioned. Even a polygon with a few dozen sides is hard to draw. One with a mega number of sides needed to show a Moser is a physical impossibility. It would be distinguishable from a true cycle event at the subatomic level. Yet, despite its impracticality as a kind of mathematical shorthand, Steinhaus-Moser notation is important in revealing how potent recursion can be. In fact, it's one of the earliest systems to be devised that can take us into same territory as something called fast-growing hierarchy. We'll have much more so say about this type of hierarchy later, because it's the most widely accepted and proven method of reaching some of the largest numbers that can be well defined in all mathematics. But we needed to approach it gradually, step by small step, as we'll be doing in the next few chapters, in order to understand it properly. Already in our travels, we've come across numbers that are way too big to grasp in the entirety with group with our brains, a billion or even a trillion we can dimly imagine. But something as huge as the mega never meant the Moser dwarfs our ability to comprehend it. Anything that's outside our ability to sense of experience directly poses an intellectual change. We face similar obstacles in trying to grasp the goings on the quantum world of the scale of the cosmos. The best we can hope to do is follow and understand the steps by which numbers such as mega and Moser are clearly and unambiguously defined. This raises an interesting philosophical point, one that we'll come back to in more detail later. We said earlier that we can prove beyond a shadow of doubt that the mega ends with 42656, that we can never know how it starts and what almost all the digits are that follow. We can say that the mega exists in some sense because we can define it exactly. Is equal to 256 raised to a series of power of 265, a power tower that's 256 levels high. This description is enough to pin down a specific number, but here's the problem. If the number so described can never be written out in full in decimal form, and if the overwhelming majority of digits are unknown and in practice unknowable, what's the status of its existence? If if this if it's impossible, the real world we inhabit, ever to discover what the first digit of mega is, what can we say about its nature? Is that first digit a number between 1 and 9, like most of the rest of mega, in some probabilistic state akin to the uncertain position of an electron in an atom? That hardly seems reasonable. Math isn't governed by the rules of quantum mechanics. Is its existence confined to some platonic universe of mathematics outside of the physics realm? To put the question more generally, whereabouts are mathematical objects before we've established with our minds or machines the exact nature of value? The Greek philosopher Plato maintained that abstract objects can exist independently of their own accord. In other words, say Platonism, there's a third realm distinct from the outer world we can sense and the inner world of consciousness. Most mathematicians go about their business content with its idea of Platonic realm, inhabited by such things as numbers. But in the final analysis, when we try to understand deeply the interplay between maths, mind, mind and matter, we have to confront the issue head on. Take the Moser, take the Moser for Take the Moser for instance. It can be pinned down in the cleverly compact form form of Steinhaus-Moser notation, and there's an easy method in principle for figuring it out. But its exact value will never be known because the universe lacks, and will always lack, the resources in time of space, matter, and energy to compute it. What does it mean, then, to say that, for example, the first digit of the mosaic exists? The first digit of the mosaic exists. Where does it exist and in what form?
Exactly the same question could be applied to the decimal expansion of the number pi. We know precisely what pi is, its definition in geometric form. It is much easier to understand than the shapes within shapes. Definition of the motion. Pi is just the ratio of the circumference to the diameter of cycles. It starts off 3.14159 and they carries on forever in decimal form, never going into an endlessly repeating pattern. Its value has been calculated by a computer to about 10 trillion decimal places. The digits we now have somehow been brought into the physical universe, their value established for all time. Because of this, because these digits are essentially frozen and unchanging, they can be said to form a random sequence. Randomness implies uncertainty, and there's nothing uncertain, for example, about the 500 decimal places of pi. Are these digits in some sense more real than those we've yet to calculate? Think about the value of the next decimal place beyond all those that have been computed so far. We know that the next the next such number exists because we can prove that pi is irrational and therefore must have an infinitely long, non-repeating decimal expansion. But at the moment, we can say which of the digits 0 to 9 the next unknown digit is. They can't even say if it's slightly more likely to be one digit, say a 2, than any other because we don't know whether or not pi is normal. A number is said to be normal if no digit occurs more frequently than any other. So, if a number in base 10, in other words, expressed as decimal when normal, every digit from 0 to 9 over a long over over a long enough sequence will crop up with equal likelihood. In the future, we'll thus be able to add tremendously to the accuracy with which pi is known, but there will always be a next decimal place that we haven't yet figured out. No matter how fast our computers become or how long they cast away trying to calculate pi even more precisely,
will never have a will never have a clue as to what the next digit will be. Someone who holds a Platonic or realist view of mathematics would argue that all mathematical objects, including numbers such as pi and the nozzle, exist in their entirety, independently of our knowledge of them. This tends to be the default position of proportionals in the field, that all of the mathematics is somehow out there waiting, like buried treasure, to be uncovered. Quite where out there is remains a debatable point. Set against this standard philosophical view are various forms of anti-realism, which question whether math has any independent existence outside of the mind or the physical phenomena that it happens to describe. The truth is, most working mathematicians, like the majority of scientists, don't go in much of philosophy, at least at least not as part of their job, because it rarely has anything bearing on what they're actually doing. In the same way, most mathematicians have no need to think about gigantic numbers or ingenious methods of writing them. They're happy to acknowledge the numbers go on forever and that somehow, somewhere, fantastically large number exists. If they do if they do philosophize or think about curious topics outside of their specialty, it tends to be in the not in the off-duty hours when they allow their minds to roam free. By their nature, by their nature, mathematicians and scientists tend to have a playful side and solve problems, puzzles, paradoxes, and other stuff that fires the imagination are often what drew what what drew them to the subject to begin with. Scientists get hooked as kids by science fiction and by popular level books on space, subatomic physics, and the like. In the case of the authors, David was inspired when young by the like of Verne, Wells, Clark, and Asimov, whereas Agnijo's desire to become a mathematician was kindled especially by the writings of Ian Stewart. Many mathematicians were weaned on writing of Martin Gardner and Scientific American classics such as Kastner and Newman's 1940, Mathematicians and the Imagination, and more recent books like Douglas Hofstadter's Gödel, Escher, Bach, an, an eternal golden bit with highlight exotic or occasional aspects of a subject that the others may appear dry and dull. Very often new ideas about large numbers are first made public in writing in writings aimed at a broad audience. Google and googolplex, names invented by a child, entered at the popular lexicon by way of Kastner in Newman's 1940 classic. Steinhaus first described his psychonotation in the Polish edition of Mathematical Snapshots, published in 1937. Martin Gardner, in his moody Mathematical Games column, introduced the world to the other ways of representing mind-bogglingly big numbers, which might otherwise have remained in obscurity. Sub-outsized numbers and ingenious aims for reaching them were displayed by mathematicians in their spare time, almost as an amusement. Others arose from a definite reason, therefore to solve a particular problem in maths. This was the case with Q's number, which we met in the last chapter. At the time of its announcement in 1939, in 1933, it was the biggest number ever put forward in the context of serious mathematical research. He held that title for about 40 years until it was supplanted by a number so large that it will take us a whole chapter to fully appreciate.